have area of the primitive cell. See, this is the primitive cell I have like this. This is like a parallelogram. How many parallelograms you can have? You can only have 3 parallelograms actually. 3 times the primitive cell volume will be unit cell volume. This is always true for hexagonal lattice in 2 dimensions actually. So that will be the 6 into root 3 by 4 into root 3 whole square. Simply multiply this quantity 3 into root 3 by 2 a square by 3. That will get 9 into root 3 by 2 a square. That's very easy. Okay, 3 times of this. Or you can calculate it as 6 equilateral triangles. One equilateral triangle in this lattice is not a primitive cell. 2 equilateral triangles together gives you primitive cell. Okay. I think you will have to try do it by yourself somewhat. Otherwise, it's of let me look at it. Then what are the 4 and 5? That solves 4 and 5 for you actually. Then 6. 6 is actually 1, 1, 1 plane. It's simple cubic unit cell. Okay. Let us go to that 1, 1 plane. You see, I have showed here. Are you able to see the screen now? That cubic structure? Because I am switching between 2 different things. One is the problem sheet, other one is a slide actually. Are you able to see the slide? Yeah, yes, okay. Okay, that's fine. Because when I'm switching, it may take some time to switch for you. Yeah. Now you see, I have showed the simple cubic structure here. I want 1, 1, 1 plane. 1, 1, 1 plane means it makes intercept A. This is the plane, the triangle actually, right? The plane I am showing you purple color. That is the plane we have. Now, my question is, if you take this plane, because any plane in 3-dimensional crystal or lattice will become a 2-dimensional lattice actually. Because this is you have points on the corners of the triangle. Basically generate a triangular lattice, right? If you keep on extending it, transfer. So put 1 dot here, 1 dot here. If you extend, you will get a triangular lattice. Triangular lattice is nothing but hexagonal lattice actually. We don't usually call it triangular, but if you just generate many points just from this triangle, you will get again hexagonal lattice. But what is the side of that hexagon? That's a different thing. What is the side of this hexagon? What is this side? That is the face diagonal. A square plus a square square root, right? A root 2. So this will be a root. Each side of the hexagon will be a root 2. We will generate a big hexagon. Okay. So that means 1, 1, 1 plane in cubic crystal is a hexagonal lattice. That's what with the side a root 2 actually. With side a root 2. Because the a root is coming from this from the face diagonal, you can calculate it. All the faces have the same length for the diagonal. So you can get that a root 2. Okay. It will simply generate hexagonal lattice. If you want to know how you say it is hexagonal lattice, just take the triangle and keep on translating points, more and more points to generate. You will see everywhere hexagons are formed. Okay, that you can easily realize. I don't know why I have written 2 times. That's okay. So effective number of lattice points in the triangle. Suppose if I take this triangle, the 1, 1 plane of this one, or I have shown the triangle here also. What is the effective number of lattice points? Because this triangle is actually having 60 degrees, which is an equilateral triangle, right? That means at each corner, we have 6 triangles, right? At each corner, we can have 6 triangles of that. That means each corner is shared by 6 triangles. Okay, because this equilateral triangle, this is not 120-degree angle, it's 60 degree. If it's shared by 6 triangles, that means each one will contribute 1 by 6. How many points are there? 3 corners, 3 points. 3 into 1 by 6, that is 1 by 2. So in this triangle, effective number of lattice points is only 1 by 2, half actually. Okay. If it is 1 by 2 lattice point, it cannot be primitive cell. Primitive cell will be double of that actually. It cannot be taken as primitive cell because primitive cells have one single point, not half point. Anyway, that's not the issue here. But this is effective number of lattice points in this triangle is half. Okay. So that's what was asked probably. Yeah. And area of the triangle, how much is the area? Because root 2a is the side, root 3 by 4 into root 3a whole square, root 3 by 2a square, that's what you get. Okay. Then number density of points they asked actually. How to find number density of points? Number density of points means number of points per unit area. Because I know the area of the triangle now that I have calculated root 3 by 2a square. I know the number of points, that is half actually. Half divided by the area. that is 1 by root 3 a square. This is the number density of points in 1 plane of simple cubic lattice. So it's nothing actually. Once you have the triangle, you have to know how many effective number of points are there. And that the effective number of points divided by the area, that's it. Very simple. You can know the plane, how it is oriented, and how the distribution of atoms are there. Suppose sometimes if an atom is falling at the center, then things will change, because then you have one effective one atom is present, but not here. There is effectively 1 by 2 atoms. That's very simple. Or if you are interested, you can calculate from this also, from the total hexagon. If you take the total hexagon, each corner will be shared by 3 hexagons. So each corner will give effectively 1 by 3. 6 into 1 by 3, how much is that? That is 2. But 1 is there already at the center. 2 plus 1, 3. So you have 3 lattice points in total hexagonal unit cell. You calculate the area of the hexagonal unit cell, 6 into root 3 by 4 a square. Then again you calculate, you get the same number density, whether you calculate using the triangle or using the bigger unit cell, it doesn't matter. Number density is a constant. So this way you can calculate the number density. Here number density means number of lattice points per unit area. If you talk about three-dimensional cases, because we are talking only a plane of a three-dimensional crystal, so it becomes a two-dimensional lattice. That's why you get number density is number per unit area. In 3 dimensions, number per unit volume. In 1 dimension, you can have number per unit length. That's called number density. Okay. So let us look at the next one. It's very bad that you have not looked at it actually. Okay, 6th one is done. What is the number density? Yeah. Repeat question 6 for body-centered cubic lattice. This is a very nice thing actually. If you take body-centered cubic and take 1, 1, 1 plane. Okay. So let us go back and go for body center. Yeah, this is body center. Yeah, I have not written anything here because you people, I want to ask you some questions. Suppose I have again drawn BCC unit cell. One that point is there at the body center of the cube. Yes, that's what BCC means. Okay. Now connect again. Same plane is same. 1, 1, 1 plane. Now my question is, if you take 1, 1, 1 plane in the cubic system, okay, will the body centered point reside on the plane or no? Somebody has to answer. You have to think and answer. Okay, just think about it. My question is this: you take a cube in 3 dimensions. Don't worry about crystal. No, that's not required. You take in 3 dimensions. What is the equation of the plane? Because it is intersecting at A. That means x plus y plus z is equal to A. That is the equation of the plane. Okay. Now we have to justify that body-centered point. Does it stay on the plane or no? Who will say? Let's think about it. Is it lying on the plane or no? Are you able to hear my question? Yes, the same plane I told, same question we have to solve for the BCC. Yes, that's why I said X. Really? How did you justify? Yes, you can. It's unit, not unit cube. You cube with side A. Yeah. So what? Yeah. And do you say that it is residing on the plane? What is the equation of this plane actually? In XYZ? Yes, Swaroop? What is the equation of this plane in terms of XYZ? If the intercepts are known, you know that x by a plus y by b plus z by c is equal to 1, right? Yes or no? Yes, but all intercepts are same a. That means x plus y plus z is equal to a. That is the plane, right? Yes. Now you tell me, on that plane, the body center lies or no? Body centered point. But what are the coordinates of the body centered point? What are the coordinates of body centered point? You have to, you can. No, not one. I am saying side is A. No, not A. No. No, no. Body centered coordinates I want. It's at the body center. Edge side
Sir,
is A.
half.
A.
A by 2, A by 2, A by 2.
Yes, A by 2, A by 2, A by 2. Substitute in that x plus y plus z is equal to A. Does it satisfy?
No, sir, no, sir.
It doesn't satisfy. Actually, it's more than A, right? And it's a
Yes, sir.
substitute 3A by 2. That means it lies above the plane actually.
Yeah, yes, sir.
It lies above the plane. So that point does not lie in that plane actually. That means 1, plane for simple cubic and body centered is same. There is no difference. Do you understand that?
Yes,
We have done for simple cubic, and for body centered also 1, plane is same actually, because body centered point does not lie on that plane. Is it right or no? 1, plane. I'm not saying whole crystal. See, lattice is different, but particular plane, if it does not have that body centered point on the plane, whether you take 1, plane of a simple cubic or 1, plane of body centered, it looks the same because only corners are occupied for the triangle, right? Yes or no? You think and tell me, all of you. सोचो कुछ, सोचते नहीं क्या तुम लोग? सोते हैं? Sleeping, so it's a natural phenomenon, right? Everybody sleeps. Do you agree with that or no? People become very silent actually. I've said 1, plane of BCC is same as 1, plane of simple cubic because body centered point does not lie on this plane. Yes, Swaroop? Yes, Swaroop चला गया क्या? क्या हो गया? Are you people hearing me or not? Are you people hearing me what I say? Yes?
Yes, sir.
Yeah.
Yes.
Yeah.
Yes, sir.
Okay. Then you have to answer my questions then. Are you understanding something? I said that 1, plane does not have the body centered point. When it doesn't have that point, whether you take a simple cubic lattice or BCC, 1, plane will be same. Okay? So whatever we did for 1, plane of simple cubic, you can do the same thing here. Exactly same drawing. You will generate hexagonal lattice again like this. All the points, everything is same actually, because body centered point does not lie on the 1, plane. That will answer for, because I don't want to keep the solution here. I want you people to think actually a little bit. That is very all of you know already 3-dimensional geometry and all these things, right? You can try to understand. Don't try to remember things. That will not help you. Because these things are, you have to try it out with your hand, try to see whether you can understand it. Because otherwise what will happen? Every time you try to remember, so you will accumulate so many things in your brain, ultimately that will saturate. Okay, so that's not happen. You try to understand, then you don't have to remember. Once you understand, you don't have to remember. So otherwise you just take it from me for granted that 1, plane of simple cubic is same as 1, plane of body centered cubic, because body centered point is not falling on this plane actually. Okay, so whatever we did for problem 5, same thing can be done for this also. Okay, so let's look at, I think you are worried that I'm asking questions, right? Anyhow, see, actually generally what happens, as most of your students and particularly BSc students, see, when a class of students are there, we have many students, many different students. Somebody like math, somebody likes something, somebody like dancing, somebody likes music, somebody likes swimming. Different varieties of students we have. You know, in our MSc also I always see people who have different things. Somebody sings very well, somebody is liking music, somebody likes magic. So different variety of students are there, and somebody likes math, somebody likes something physics, somebody likes literature. All people are there in physics. That's what I'm saying. It's not that physics does not mean that everybody likes physics, not necessarily. People have come into physics somehow, sometimes by force or something, or there is no other option, so they came or something happens. So when you conduct a test, because test is conducted in the college or university, when you conduct a test, same test you are giving for all. Now about this testing, somebody has given an example, an analogy actually. Suppose imagine that in a forest, you have a tall tree, very big tree. Okay, it's a long tree you have, and you gather some animals there. You gather a lot of animals like elephant, lion, tiger, and snakes, all possible animals. Snake, cheetah, okay, leopard, and maybe squirrel, and monkey, etc. All these animals you gather, including birds. You gather all the animals. They actually represent a class now, exactly, somewhat analogical, because they cannot come and sit in the class anymore. But you can analogically take that these are all have different capabilities, right? Elephant has some capability, tiger has a different capability, the bird has a different capability. Now the question is, all of them have to climb the tree. Who climbs first? That is the test actually. Now the problem is, you are not worried whether somebody know climbing or no, but you are doing a test where they have to climb. Who climbs first? Maybe monkey will climb first, or bird will climb even much faster. It will not climb, but it will fly. Okay, or other things may try a little bit. Snakes and other things may try to climb, but those who cannot climb at all, what they will do? So the problem is like this. In any class you take, physics or math or any subject, I am not talking about subject here, because if you have 50 students sitting in the class, 100% sure that it's not that everybody likes physics and they're coming. No, not that. They are coming for some, there are many reasons maybe, but somehow they have come sitting in the class. Now for all of them you conduct the same test. It is like the tree, the climbing and stuff. Somebody who likes physics, who is interested, definitely can do that. Those are not interested. They don't want to do it. But they have other activities. They don't want to do. Does not mean that they are incapable. Their capabilities are not matching with this, what test we are giving. In that case, they will not be able to do anything. For example, what lion will do there sitting there? You ask her to climb the tree, long tree, that vertically up. Can it climb at all? But we think that it is incapable. It's very capable. It can eat away all the animals at a time if it wants. It can eat. Okay. So the problem is, in a classroom, taking so many students, and everybody is given the same test, and we compare and grade them and say that this fellow is bad, this fellow is good. So the problem is, in terms of physics or some mathematics, maybe you can say this fellow is poor or something. But the point is, testing, way of testing, our education system is not very good actually. The problem is, it's not that everybody is interested in that. If everybody is interested, then your testing is okay. Otherwise, what will happen if lion wants to climb the tree? It keeps learning from today, let's say, how to climb. Will it be possible for it to climb even after maybe 10 years? That's not possible. So those who are fit for certain things, they have to. My point is that if they are not really interested in some particular subject, you don't hang around all the time. You should see where you are interested. In that area, you have to focus it. Okay, anyhow. So, yeah, where we are now, that is, that's very simple. Yeah, now justify whether the body centered point lies on the 111 plane or not. I have already told you that does not lie. It lies above the plane. Then let's come to problem 8. In FCC lattice, what kind of two-dimensional lattices are generated by the planes? Different planes I have given, variety of planes, 111, 100, 110. Find the corresponding primitive lattice vectors, primitive and unit cell volumes, everything, area, number density of points. How to do that? Just let us do it quickly, because I will not ask you now what to do, because you have no response, right? Yeah, doesn't matter. Now you see 111 plane. Is the triangle what I am showing here. Triangle, but now it is an FCC lattice. So each face center has a point. Now you have a triangle, similar triangle, whatever you have in simple physics, but the middle of the edges are occupied now. This one like this. That means each edge has 3 points actually. Two at the corners, one at the middle. Okay. So this is the triangle. But how many lattice points are there effective in this triangle now? Because corner atoms contribute 1 by 6 into 3, that is half. Okay, these three, each one contributes half. Edge is shared by 2. So half, that is 3 by 2. Plus another 1 by 2, 4 by 2, that's total effective number of atoms is actually 2 here in the triangle. What is the area of this triangle? This is a root 2, right? Side is a root 2. You can calculate the area, already have calculated earlier. So that number 2 divided by area of this triangle, that will be the number density. And lattice generated is again hexagonal lattice, and you see these points you connect and see, you will get hexagonal units selected, just like this. This. So it's hexagonal unit cell. Okay, this plane also generates hexagonal unit cell, but number density of points is more actually in this plane now compared to simple cubic or body center. Then I've also given you 110 plane. 110 plane actually looks like this. You see that rectangle I have drawn. That is a 110 plane. It should intersect in 2 axes, and third axis no intersection. That is 110. Okay, intersection on third axis is infinite. That's 110 plane. 110 plane looks exactly like a rectangle. Actually, I have drawn the rectangle here. You see, this is the rectangle. Okay, so rectangle, it is points are there at the corners and also middle of the sides. Okay, so in this again, corner points will contribute 1 by 4 each, because each corner will be shared by 4 rectangles. 1 by 4 each. 1 by 4 into 4, that is 1. These 2 atoms will contribute 1. So total number of effective lattice points is 2. And area, you find out what is the area. This is actually, you know, this is actually side A equal to A, and this will be face diagonal, that is a root 2. A into a root 2, that's the area. A square into root 2. That 2 divided by a square root 2, that's the density of lattice points. And then I have also given you 100 plane. 100 means one of the faces you look at, any face, it doesn't matter. You take this face on the right side, that will have a square, points with the corners, and one at the body center. Okay, so this is square, one at the body center. But what kind of lattice is that? You should not call it body centered square, because there is no such lattice actually. But body centered square, centered square is same as square again. You just take this center and connect it to these 2 corners. Another center you take here, that will also be a square. This is also a square actually, which I will put it as light lines. That is also a square, so you should call it square lattice. So this 100 plane makes a square lattice. Okay, 100 plane, this becomes a square lattice. But what is the side of the square? Not A. This you have to calculate. This is actually a root 2 by 2. That is A by root 2. So it is a square lattice with the side A by root 2. That's what we have to do. Okay. So I'm not providing you solution, just I'm giving you hints what to do. Okay. And how many atoms are there in this square? How many lattice points are effectively present in this? 4 corners are giving you 1 at the middle, that is 2. 2 lattice points in the square. 2 divided by a square, that is the density. 2 divided by a square, that's the density of lattice points in 100 plane. Okay. Okay, this, yeah. Now this is actually, I did not put the question here. So here, question number 9. What is question number 9? What is the shortest? Forgot. Question number 9 is, what is the length of the shortest reciprocal lattice vector of the BCC Prevalence lattice? First, we start with BCC Prevalence lattice and reciprocate it. Once you reciprocate, you will get FCC, that we know already. Okay. How many vectors are there with the same length? Let's look at that. It's very easy. Because you already know that your BCC, if you take BCC primitive lattice vector A1, A2, A3, and you reciprocate it, you will get B1, B2, B3, which are looking like face-centered cubic lattice, right? These are face-centered cubic lattice actually, because reciprocal of BCC is FCC. So FCC has how many nearest neighbors? In FCC lattice, we have 12 nearest neighbors. In one of the lectures I have showed you in the diagram actually. FCC lattice has 12 nearest neighbors. Okay, that means, what does it mean? See, when you have when you talk about shortest reciprocal lattice vector, see B1, B2, B3 They are also reciprocal lattice vectors. B1 is a primitive lattice vector. B2 is also primitive reciprocal lattice vector. B3 is primitive reciprocal lattice vector. So all these three, you can call them prevalence vectors also. These are the shortest prevalence vectors. You can see for any lattice or a reciprocal lattice vector. If you are in the reciprocal lattice, you call it reciprocal lattice. If you are in the prevalent lattice, you call it prevalent lattice. But always primitive lattice vectors are the shortest prevalence vectors or shortest reciprocal lattice vectors. So these are the shortest one. But as we know that if you take one point, the FCC lattice, FCC because we have got FCC lattice from the BCC. We started with BCC and we got FCC. In the FCC lattice, each point is surrounded by 12 nearest neighbors. They are at equal distance. That means if we draw a sphere, that will contain all the 12 points actually. They are spherically distributed. Okay. So what are those coordinates of those 12 points? You just take these vectors 2 pi by into j plus k plus I plus j, make it plus minus. All of them have the same magnitude. See, whether it's plus or minus, magnitude is not going to change. Only directions are different. Okay. Suppose I have 2 pi by into j plus k. I can also have 2 pi by a into minus j minus k also, or plus j minus k. All these plus minus if you include, you will generate 12 vector sector, 12 reciprocal lattice vectors. All the points will lie at equal distance actually. That's the nearest one. Yes. What happened? Any problem? Somebody wants to say something. Yes. So if you take that B1, B2, B3 primitive vectors and make it plus minus now, because we are for B1, B2, B3 primitive vectors are okay. If B1 is a primitive vector in the opposite direction, then always have a vector in the opposite direction. That is minus j minus k. Okay, 2 pi by a plus minus j plus minus k plus minus k plus minus a plus minus a plus minus j. This total will give 12 possibilities, because here plus minus j will, how many will come here? 4 vectors will come. Here 4, here 4. Total 12 vectors will come. All the points will be at the equal distance. What is the distance also you can calculate? 2 pi by a into square root of 2. The distance from the origin to all these vectors is 2 pi by a into square root of 2. That is the nearest neighbor distance in reciprocal lattice of BCC. Okay, just think that when you have primitive lattice vectors, the shortest regular lattice vector possible is primitive lattice vector itself. That's the shortest one. Okay, so all these three have the same magnitude, right? 2 pi by a into root 2, 2 pi by a into root 2, 2 pi by a into root 2. They have the same magnitude. All of them are shortest reciprocal. Not only these, apart from that, if you take other vectors which are rotated, you rotate them, you get other vectors. All 12 of them have the same magnitude. That is 2 pi by a into root 2. So basically that's because of 12 nearest neighbors in FCC lattice. But the next one problem that is for the BCC. That's the same thing you can do here also. If you start with FCC lattice, then you will get BCC reciprocal lattice. BCC reciprocal lattice vectors are like this. B1 is equal to 2 pi by a into j plus k minus I minus j minus k. Now again the same thing you can do. All these vectors have the same magnitude. 2 pi by a into square root of 3, 2 pi by a into square root of 3. So they are at the same distance from the origin. B1, B2, B3 points at the same distance from the origin. But because in BCC lattice, you have 8 nearest neighbors set. All 8 you can get it just by 2 pi by a, making it plus minus j plus minus k plus minus I. Why? You don't have to make for others like what you did there, because all the vectors contain ijk here. If you make it suppose plus minus j plus minus k plus minus I, are you getting this one I plus j minus k? You see, if you take this one plus, this is also plus I plus j minus k, you can get all possible. You can generate everything. All these 3 plus another 5. Everything can be generated by this. That is the, what is the length of this vector? 2 pi by a square root of 3. That is the length of the shortest reciprocal lattice vector in the FCC reciprocal lattice, that is BCC system. So like this you can check. So these are the problems. Probably one more is there, I think. Yeah, this what's the 10th one? I don't have. Problem 10 is that FCC only, no? Yeah, that's fine. Yeah, That's done. Then let me just review a little about one-dimensional prevalence, because I have not told you about that. It is very easy. So if you have one-dimensional prevalence, that means you have chain of lattice points separated by a distance a each, like this. Let us take it along x-axis. BL means that's a prevalence. Okay. What is the primitive lattice vector here? I can simply take it as a vector is equal to a into I cap. That is only one primitive lattice vector is sufficient to scan one-dimensional lattice sector, because you have to only go along one direction. Now, if you reciprocate it, your length, distance between the points will become 2 pi by a simply. And if suppose it depends on a is how much. Suppose if a is equal to 1, what is 2 pi by a? 2 pi by a is 2 pi. You will stretch the lattice sector. Suppose if a is equal to 0.1, then 2 pi by 0.1, that will be 20. Then also you will increase. If a is less, your reciprocal lattice length will increase. If a is very high, then you have less, because you are inverting it basically. Okay, it gets reciprocated. If a is more, you will have less here. If a is less, you will have more. Something like this it works. So you have again one-dimensional lattice and reciprocal also. You generate a one-dimensional lattice and keep along the same direction. The distance lattice parameter becomes 2 pi by a. That's the only difference. Now this primitive reciprocal lattice vector, you want to write it B, that is 2 pi by a into I cap. Original lattice is a into I cap. So that means in one-dimensional lattice, what will happen is just lattice parameter gets inverted with a multiple of 2 pi, 1 by a into 2 pi. That's what it is. Then yeah. So and one more thing I just want to show here. Okay, let us take suppose one-dimensional Bravais lattice again. I have just drawn one purple colored line around one point actually. That I have started in the middle of these 2 points and it has gone up to the middle. That has a length A actually. This has a length A, starting at the middle of this to the middle of this. Okay, so that colored and equal this length is A and contains one lattice point. Within that length, how many lattice points are there? You have only one lattice point. Okay, so this cell has a lattice point at the center, and this is called Wigner seed cell. In one-dimensional Wigner seed cell is very simple. Just bisect this A here, bisect it here. In between whatever is there, that's called Wigner seed cell. Wigner seed cell is a primitive cell because it has only one lattice point, but the lattice point is at the center of the cell here, not at the corners. Because earlier I told you primitive cells, ordinary primitive cells have lattice points at the corners, but this will have lattice point at the center. Okay, so if you have a lattice point at the center, so only one lattice point in this length A. Okay, that's called Wigner seed cell. You can define it in 2 dimensions, 3 dimensions, everything, but basically it is like this. Okay, if you take this lattice point, whatever is at the center of that purple line as origin, then Wigner seed cell goes from minus a by 2 to plus a by 2. The Wigner seed cell extends from minus a by 2 to plus a by 2. If you keep this as origin, I am saying, it's your origin. Now this I am telling because Wigner seed cell is not that much used in Bravais lattice, but the corresponding or analogical is Brillouin zone. So very important in reciprocal lattice sector. Brillouin zone is nothing but Wigner seed cell in reciprocal space. So let us look at that. Now again I have taken reciprocal lattice. I have taken this line again exactly in the same way around one reciprocal lattice point. Now this is a reciprocal lattice point. Around this I have taken. It starts at minus pi by a to plus pi by a. If I take this as origin, if I fix my origin here, this goes from minus pi by a to plus pi by a. Okay, so this is called first Brillouin zone. Actually, these Brillouin zones are very important for studying band structure. Even this chronic Penning model, wherever you go, always you talk about Brillouin zone. Brillouin zone is nothing but the Wigner seed cell in inverse space actually, or reciprocal space that you should call it. So this is going from minus pi by a to plus pi by a. That is called first Brillouin zone. You can also define higher order Brillouin zone, that don't worry now. So this is the way to relate your Wigner seed cell and first Brillouin zone. First Brillouin zone is nothing but the Wigner seed cell of reciprocal lattice. That's what you should call it. Okay. So these are very important conceptually, and another important point I want to tell you, Wigner seed cell is a primitive cell, but why don't we use Wigner seed cell in our discussion? Because we are not usually using. Suppose you imagine that, how do you construct Wigner seed cell? you connect it to all nearby points from the center point, take it as origin, and connect it to all points and bisect them by perpendicular planes. And whatever polygon you are getting, which is the closest to that center point, that is called Wigner's cell. But if you want to define Wigner's cell, for example, for body-centered cubic lattice, you have 8 atoms surrounding the body-centered atom, right? Each one you bisect, you will get the surface or polygon with 8 surfaces. It becomes very complicated. So its definition wise it's good, and also important thing is Wigner's cell has the full symmetry of the lattice also. It is very symmetric. Otherwise, generally primitive cells are not symmetric. Wigner's cell, which is a primitive cell, is highly symmetric. It is symmetric and primitive. But it's difficult to use it because it can have very odd shapes, very complicated shapes in 3 dimensions. That's why it's not much usable. But its analogical entity that is called Rayleigh zones are very well used in reciprocal space. Okay, that this goes from -π by a to +π by a in one dimension. First dimension. Now let's look at your what has happened to this. Because yesterday I think Swarup was asking about finding reciprocal lattice in 2-dimensional cases. Let us take the most general lattice, that is take an oblique lattice. Oblique lattice means we know A1 not equal to A2 and phi not equal to 90. That is called oblique lattice. This is the most general case. From this lattice you can get all other lattices. Suppose you make A1 not equal to A2, phi is equal to 90. You will get a rectangular lattice. Okay. A1 is equal to A2, phi is equal to 90, square lattice. And A1 is equal to A2, phi is equal to 120. You will get hexagonal lattice. Okay. And for body-centered tetragonal, triangular also you can generate from this rectangle. All rectangular lattice, everything can be generated from this. That's why I've taken the most general lattice. And what will be given if you are asked to find the reciprocal lattice for any given lattice? We are given actually A1 and A2. That will be given to you. A1, A2 is given, means vectors are given. That means you know the angle also. That means for you, magnitude of A1, magnitude of A2, and the angle is given to you. Full details are there. We are asked to find reciprocal lattice. So what is the orthogonality condition for reciprocal lattice? Bi dot aj is equal to 2 pi delta aj. We can use that condition actually. Okay. Let me. So now you look at this. A1, A2 are here. Then we have to find B1 and B2. That's the reciprocal lattice vectors. Okay. So A's and B's follow orthogonality condition. Orthogonal condition. Bi dot aj is 2 pi delta ij. This condition has to be followed. That means B2 is perpendicular to A1, B1 is perpendicular to A2, and B1 dot A1 is 2 pi, B2 dot A2 is 2 pi, B2 dot A1, because they are perpendicular, that is 0, B1 dot A2 is 0. These are the 4 relations you will get from this orthogonality condition actually. Okay. That means first we go back and see what we did. A1, I have taken A1 along x-axis simply, for simplicity only. This is, you take A1, see when you have 2 vectors in 2 dimensions, always you can fix one of the axes along one of the vectors. X-axis you fix along A1 actually. I have fixed it like that. And I can write A1 is equal to magnitude of A1 into I cap. This is the magnitude of A1 into I cap. Then similarly, if you want to write B2, how will you get B2? What will happen is when you have the vectors A1 and A2, you rotate whichever vector is down, that you rotate it up by 90 degree. A2 you rotate, A1 you rotate by 90 degree. That you will get B1. Similarly, A2 you rotate by 90 degree in the opposite direction. That you will get B2. That's what the way it works actually. A1 should be rotated clockwise, anti-clockwise, to get B1. A2 in the clockwise to get B2. Don't rotate them in the same direction by 90 degree. That doesn't help. When you rotate them in the same direction rigidly, the angle between them is not going to change. That you will not get reciprocal lattice. How do you know this one goes, so one rotates clockwise, one rotates anti-clockwise? Because you know that if you want to get B1, what is B1? That is A2 cross A3 by some constant A3. A2 cross A3 means A3 is, you have to imagine that A3 is perpendicular. A3 is perpendicular. A2 cross A3 gives the direction like this. It will be perpendicular to A2 in perpendicular to A3. But that is not important here. You can just use these relations and find. So always remember it that whatever is the vector which is below should be rotated up, and vector above should be rotated down. That's the way it works actually. By 90 degree. Both will rotate by 90 degree. Yeah. With that information, let me take B2. Now you see what happened actually here. If you rotate A1 by 90 degree, you will go along y-axis actually, right? That means your B1 is along y-axis, positive y-axis. That's why I have written it as B1 is equal to. No, that we should call it B. By mistake I have written B1 or what? B2, sorry. It is actually written there. I made a mistake. This should be B1. When you rotate it this way, this should be called B1. This should be called B2 actually. Which we generate from A1 should be called B1. This is B2, but there I have inverted it by mistake. Yeah, that's okay. But you know that's not going to make a change. If you write B2 as B2 into J cap, what is A2? Just look at A2 here. A2 is making angle phi with x-axis. Okay, that vector can be written as A2 into cos phi I cap plus sin phi J cap. Then vector perpendicular to A2. If you want to write a vector perpendicular to something, suppose I have vector xi cap plus yj cap. What is the perpendicular vector? Just change the sign of one of them and change. Suppose for this vector I will write sin phi I cap minus cos phi j cap. That will be perpendicular vector. Just interchange and put a negative sign. This way you can generate a perpendicular. So vector perpendicular to A2 is A2 sin phi I cap minus A2 cos phi j cap. You see that cos phi sin phi is interchanged and there is a negative sign. And if you want to find the unit vector perpendicular to A2, that is sin phi I cap minus cos phi j cap. Okay. Similarly, if you write B1 now, B1 is equal to magnitude of B1 into sin phi I cap minus cos phi j cap, plus multiply the magnitude with unit vector along the direction. Okay, because B1 is perpendicular to A2. Then what is B1 dot A1? That is 2 pi. That will give you A1 B1 sin phi is equal to 2 pi. B1 is 2 pi by A1 sin phi. That's the magnitude of B1. But what the direction that is given here? Sin phi I cap minus cos phi j cap. If you want vector B1, 2 pi by A1 sin phi into sin phi I cap minus cos phi j cap. Similarly, B2 dot A2 is also 2 pi. That will give you B2 is 2 pi by A2 sin phi, but B2 is along y direction. That is 2 pi by A2 sin phi j cap. So we can actually use these orthogonality relations and find, but instead of that, for simplicity, what people do, you take A1 A2 vectors. There is no A3, but you take a unit vector along z-axis and make A2 cross A3, A3 cross A1. Like that, you make and find this. Then it becomes easy for you to handle it because you can use the same relations. But here we are starting with orthogonality relations. But these two vectors, what I have given for B1 and B2, it will work generally. For any lattice, it doesn't matter. You just only define your phi, angle phi, and A1 A2. If A1 is equal to A2 and phi is equal to 90, you get a square lattice. Just substitute it there and see you immediately get B1. This can be used in general. But generally people don't do it that way. For finding these vectors, you always assume that there is a vector normal to the two-dimensional lattice, that is your A3 axis. So just find out if it is B1, A2 cross A3. A2 is known to you. A3 is K cap. You are taking Z cap direction, K cap direction. That is A3 cross K cap. That will give you your B1. Similarly, other vector for B2. B2 is equal to, I will get B2 is equal to A3 cross A1 by some volume of the primitives, right? Multiplied by B2. So that's why that is a technique to do. But actual way of doing is this. You can use this as a general relation for B1 and B2 in terms of phi, A1, A2. And for special cases, you can always do. If A1 is equal to A2, phi is equal to 90, you have a square lattice. A1 is equal to A2, phi is equal to 120, you will have a hexagonal lattice. Like this, you can generate all the lattices from this. Okay. So that's what I wanted to say today. But let me also tell you something. If BSc students are thinking, because see, this is usually not dealt at BSc level, not so much in detail. You may know something little about reciprocal lattice and all these things. At least I have studied all these things when I was doing PhD in detail. Because when we joined for PhD in UGCDSS or Indo, the first task I was given is I have to discuss about reciprocal action during the coursework. Sometimes they arrange some lectures kind. Student has to talk. I was asked to talk about reciprocal action. That time I didn't know anything. After my MSc, reciprocal action means except B1 is equal to A2 cross A3, B2 is equal to A3 cross A1, and B3 is equal to A1 cross A3. Except these things, I have no idea. Reciprocal action. So you have to study that time. So for everybody, it's like that. At BSc level, you don't expect you to understand everything. So this I was discussing about this two-dimensional act, reciprocal action, because Farooq was asking yesterday. You can always do it this way if you want, but easier way is assuming a unit vector along k cap direction. But again, your unit cell, primitive cell, everything is plane only. You will get area only, not volumes. They are not making it three-dimensional. Only for convenience, you use a k cap direction to get the vector sector. You just you can use the same relations. You don't have to derive all this. But once you derive this B1, B2, just substitute. You get your lattice for anything. Only different values of phi and A1, A2 you need to know. Okay, so that can be done that way. So otherwise, generally, even at MSc level, these questions are asked actually in some entrance exams. For example, GATE or CSR. Sometimes they give a lattice for two-dimensional lattice. They ask you what are the reciprocal lattice vectors. First of all, what are the primitive vectors? How will you find? That itself becomes task. It's not easy actually sometimes. Okay. So, but anyhow, that comes later. And if you understand it conceptually, you can always do it, whatever technique it is. That is very important. You must try to understand. Spend some time, try to read and understand. Okay. From the BSc level, if you start understanding about the lattice and this thing, that is better actually. We are also teaching at MSc level. I teach the same thing, almost same things at MSc level actually, MSc first year. So when we do in the classroom, I was teaching, so usually people don't speak much in the classroom. When I ask something, maybe somebody responds, so they may not respond. But in between, because of this corona, we started online classes. Online classes, people become very bold actually, because we are not seeing them directly. Teacher is not seeing them directly. And they become like scientists actually. Suddenly I have seen that many students, they start asking questions, why this is happening like that, something, because they are hiding and talking now. Because they are not in the classroom. But somehow these participants are not like that. Whether I see you or not, probably are very silent. But MSc students I used to see, they talk like scientists from home actually. So घर पे बैठ के बहुत energy आता है इसमें. He becomes great. क्लास में पूरा बिल्ली जैसा बैठेगा. कुछ भी नहीं बोलेगा. So this somehow these online classes made some people, some students very bold actually. They ask questions. अगर क्लास में कभी मुँह नहीं खोलेगा. But घर से बहुत बोलेगा. So, but anyhow, you people are not talking in any case. Anyhow, that's not the problem. But what I want to tell you is spend a little time and read some good books. For example, you people should read, at least BSc level they are talking. You read about Decker, A.J. Decker, Solstice. Kittel is too hard, maybe too high for BSc level, but you read A.J. Decker. It's a very good book. And spend some time, read. If you understand more and more, you will enjoy also. If you understand, you read more. You read more, you understand. Cyclic. You don't read anything, then you don't understand. So nothing happens. But if somebody is interested, spend time with some good books actually. Right? Particularly A.J. Decker, Kittel. And Kittel maybe for MSc level, but Decker is okay. You can read it. It's a very simple book actually. So try to read that kind of books. So in the next class, I will talk about X-ray diffraction. I could have started it today, but I thought we'll discuss more on this problem, but somehow you people are not responding. Otherwise, I would have done much more discussion of the problems actually. Anyhow, that's not the issue. But what I want to tell you, try to spend a little time. Read the problems at least. See, sometimes what happens, if you read the problem, to understand something. At least you know that such a problem exists. And you look at your GATE or the CSR problem, sometimes they are based on these fundamentals only. I have given very, very basic questions. Whether you understood or not, that's what it tests you. But probably you have not spent time because it was given in the time late in the night. Probably you didn't spend, but just go through that question. And if you have more problems, you can discuss with me. You can put it in the group also. If somebody has a doubt, you can put it in the group. Okay. So we can discuss more. That's not issue. But problem solving is not important. I'm not saying that is important. That actually tells you whether you have understood something. It is only test or understand. That's what it will do. It will only tell you whether you have understood something. You have to test it like that. So try to focus on concepts, go step by step. Don't jump onto problems, do problems. Somehow people try to do problems, that doesn't help it. Because if you solve 100 problems, then you will stuck up in 101 problem again. That is of no use. Better to understand all basics properly and solve the problem. Once you understand the concepts properly, you will find many ways to solve a problem. Okay, but otherwise you get some coaching material here and there. You try to solve one problem. You only know one way because you are not understanding. So that understanding is very important. Even for just exam, I will look at the just questions actually. They are based on very basic understanding. So that is a problem with us. It's the same for me also. I was also not understanding everything, and now also nobody understands everything. That's what is thing in physics. Everybody has to be humble. Nobody can say that I have understood everything. Even great Einstein did not say that he has understood everything. So we are nothing like that. So, but my point is, if you are interested, spend time with some good books. Don't read books which are non-standard. I don't say particular book or something, but always take a standard book and read. And if you are reading any book, it is okay. See, book which is accepted by our scientists, it is okay. But if you don't read some book which misguides you, because if you don't understand, it is fine. If you don't understand, there is no issue. But if you misunderstand, it's a big problem actually, because you go in a wrong way all the time. So misunderstand. That's why you should read standard books always. Read a book and talk to your teachers and try to think about problems and see it. Because at least in this area, I know that people are more interested in physics. Generally, more research, that's what I see. In Andhra and all, nobody cares about physics. Nobody talks about IT or something. It's very rare that people are so interested in physics. But here, a lot of people are there with interest in physics. But the problem is, don't mug up things. Mugging up and writing, that is not useful. Don't read only for exam. Exam is important. You have to pass the exam, you have to get good score, that is okay. But that alone is not sufficient. Apart from that, you should have your personal reading and interest. Okay. Okay then, if you have something, please ask, otherwise I will close. The Decker book is the soft copy is available freely. Yeah. Anybody? Yeah. Yes, who is speaking? Okay. Yeah, please ask them if they want something. We can discuss. Yeah, that's okay. Yeah, no problem. Yeah. So tomorrow we'll start with X-ray diffraction. Okay. Yeah. Okay then. Yeah. Thank you.
Yes, sir.
Somebody wants to say something.
Thank you, sir. Bole.
Acha, who is speaking?
Sir, Ipsita Pani.
You are a BSc student or?
Yes, sir.
Okay. Yeah, okay, no problem. Yeah. Let them look at that question paper again. So probably they have not looked at it, look like slide. Let them look at it. If they have doubts, they can ask tomorrow. No problem. You are most welcome to ask questions. No, don't worry. If question is wrong also, it's okay. Be free. Nobody will say anything if you ask a question. Okay, you can ask. You just keep quiet. Also, no issue. It's up to you. You decide. But asking question is not a big thing because you are sitting at home. No. You are like a king actually. You are not in the classroom, right? So you can ask any question. Nobody is seeing you, right? Okay. Yeah, that's fine. Yeah. Okay, then I will remove.